Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
My name is John Nordlinger from Microsoft Research. I'm very pleased to introduce Young Kao from Virginia Tech. Young comes from UCLA and also Electronic Arts, where he worked for a few years. And now he's doing research on animation and speech and the relationship between expression in that genre. So those of you watching remotely and those of you here, thank you very much for attending. Young Kao.
Thank you. Thank you, John. It's my pleasure to be here, as usual, and especially after what happened on 4/16 at Virginia Tech, as terrible things happened there, and we just talked about this thing last night during our dinner, and I think I should probably put some kind of sentence about this, because Virginia Tech has this big, sad tragedy happens, but the community of Virginia Tech is very strong, and we're currently recovering from that, and the students is also very strong, and it's not like any angry against university, and the people are really encourage people and put this whole community together. So even the media is actually pushing the students, asking what their impression about what's kind of how do you think about how university treat these events, and there's a lots of big problems happen there, but we still students have positive feedbacks to all these kind of media questions. So we're okay. And also there's another thing I have to say is in computer science department lobby, we have a big picture taken from Microsoft, basically is Virginia Tech alumni, and took this picture and sent to us to show them support, and we really appreciate that. Jump back to this talk. So my current research in Virginia Tech is animation and gaming related. So I built a lab there, and I'm doing lots of interactive gaming and interactive graphics. So today's topic is about how to do very interesting expressive speech motion in this interactive environment. Several examples about what's the current status of facial animation research or applications. Especially in movies, and we see lots of very, very good facial expressions. So one's taken for so that's Mrs. Smith for Matrix trilogy, and you can see there's a lot of facial expressions put on and have very, very realistic looking. Also in Shrek and in Gollum, we have actually virtual characters. Even it's not photorealistic, but they have very expressive faces there. But look at the facial expression in movies. In those applications, normally artists spend days and months tweak about one frame to make the things really look good. So they have lots of tools and very, very realistic, but they had to pay the price of the time and very intensive labor work on top. In the game, so game industry is starting picking up on facial expressions. There's one I saw in Half-Life 2. They have the real facial expression engine in there with expressions, lip syncing, everything looking good. But the problem of facial expression in game is because facial expression is very computational intensive. So people are very sensitive to what people are looking. Then this interactive control. So how can you make the current game console and PC powerful enough to do the real-time synthesis of these facial expressions? That's a very good research area. That's what I'm going to address in this talk. Of course, there's another applications. I briefly gave overview There's medical things about virtual anatomy and virtual surgery. For example, here, if you want to plant some special kind of skeleton underneath skin, what kind of looking. And also for education and the training. And we have, for example, we have...
Where are the roller skates? That's right.
Basically, there's a very interesting education tool for the children with autism, because they're not trying to talk with people, but they tend to talk with computer. That's why people in, I think is in UC Santa Cruz, they did this demo, basically how to help the people to talk with a virtual actor. And there's another applications, military application, which are involved is at USC, we have an institute working with Department Army and doing this training for captains. So basically, we have this interface, demonstrate a video, show us some kind of interaction between the soldier and their leaders, and we ask the questions through this virtual actor. What kind of environment we have? What kind of questions you find? What kind of problem you find? And then can have interactions with this virtual actor. So there's a lot of applications in there. But as I said, the challenge of this facial expression is, if you want to do physical simulation, this is very hard because our face is deforming in so many different ways. And there's a lot of muscles, more than 100 muscles related to our facial expressions. And there's several layers of the skin, of the tissue, and with underneath bones, muscles in there. It's very hard, very complex system. And people are very, very sensitive to facial expressions, and they can be very expressive. However, very tiny motions in our, for example, eyelid, eyeball, things people are looking to that because we have this face-to-face conversation every day. You have only one small thing doing wrong, people can tell, okay, this is not realistic synthesized face. So that's this challenge over there. But altogether, put all these challenges together with interaction, basically you have a real-time synthesized algorithm to do the whole thing. It's a very, very difficult task. So in this talk, in this project, what we did is we want to synthesize a virtual character, a virtual face, which have real-time lip syncing. Basically, anything you have, just dropping, you can synthesize this facial motion. And also, we have a real-time control over what kind of expression, what kind of emotion this face has. Give an overview. So our system takes into the input, which is a speech audio.
The sun was shining brightly.
Like this. And our lip syncing module is actually a real-time search into a speech motion capture database. We record lots of motions in there. We put up the right motion and stitch them together, doing post-processing, and create a lip syncing motion with neutral.
The sun was shining brightly.
And after this, because we want to put the right expression on his face, so taking this as input, we apply an emotion mapping module that we can map original neutral face into the face with the right expression.
The sun was shining brightly.
That's our system. Okay, this is a little bit a roadmap about my talk. So first, introduction, we just talk about it, and we will discuss a little bit detail about lip syncing and emotion mapping module, and I gave a summary and talk about some kind of research, future research and related projects. Okay, first, lip syncing. What is lip syncing? Lip syncing, as I said, is we sync the audio with our lip motion, right? So normally what people do is this. So we give audio, for example, this audio signal, and we know for example, we know what this audio speak about, for example, face. And people do phoneme segmentation. Basically, the segment finds a piece of segment with this audio. Basically, they say from here and here is the phoneme f, and from this here to here this time is a. And from here to here is S. After doing this very basic phoneme thing, the phoneme, as I said, is a very atomic unit of our English language. In English, we have about 46 different phonemes in there. So basically, we can label anything we want, given the audio signal and the word. And after this, the very simple thing we can do, and so normally what industry does, is they assign each lip posture, basically a shape, or a small chunk of motion to each phoneme, basically always like. And when we're doing this, very easy, we can do, for the whole motion, we can do a linear interpretation or any kind of interpretation, then everything is smoothed out and there's a motion, right? There's a standard way industry is doing. However, the problem happens is lip motion is not like you can assign, you can build a table, say F is always this mouse shape, because our mouse shape has context dependent. For example, S in face and S in zoom is the mouse shape is different because the next phoneme has effect on this current phoneme. So that's why we cannot just build a single table. So people say, why not build, for example, two phones together like a combination table? Yes, but the thing is, this phenomenon is called co-articulation. The co-articulation can affect mouse shape 2 to 5 neighbor phonemes, can be 2 to 5 behind and 2 to 5 before that. So the combination will be enormous if we have to build a table so large. So our approach is instead of doing this kind of table thing, so we record a very common sentences about our normal speaking, and it's into this database. We're using a data-driven approach, basically, the database to find the most common used one and use this to synthesize the current input speech. That's a data-driven approach. I will discuss about this thing later on. So how to search the database for the proper co-articulation? That's a question we have to answer later on. Let's start with our system. So the first thing we have is a database. So we record a database of this guy as a Hollywood actor. A very poor actor, is not famous one, but is very expressive. And we record lots of sentences, more than 1,000 sentences, and speak so many sentences, also in 5 different emotions. Basically later on, because we want to synthesize these facial expressions in different emotions. That's why we took lots of expressions over there. And each emotion we have this 2 to 4 seconds short sentence, but they have a lot of density of marker put on the face, 109 motion capture markers, lots of data we process. So after 4 months of processing time, which I did, so we have this database. For example, what kind of database we have to build? For example, this is only one sentence. For example, this sentence only one word, face. We have lots of these sentences, thousands of them. This one sentence, what we have is we have audio signal we recorded, and we also know the what kind of text associated with the sentence. And also we have motion capture, motion curves, motion trajectories associated with the sentence. We all synchronize together, and we also know what kind of emotion we have for this sentence, because we ask the actor, say, please speak this sentence in this emotion. So we know that is emotion. So for this sentence, we align them together. We always know what start with the end. The first thing we do is a simple thing is when we get the audio, we do a phoneme label as usual. And we got audio feature curve because this curve is a very high frequency curve. We cannot use it, so we use F0, and with other features input together, we have a vector trajectory. And then we build these things called anim. This anim is encapsulate this whole thing, basically include what the phoneme label is, what is the audio feature curve fragment, and what's the emotion notation, and what is emotion segmentation. We all include this whole thing into this thing called anim. And this anim thing, when we put together, we encode the context information. As I said, the context is very important information we have to encode in here. So we use a linked list to encode this context information. We know this F is before this A, and this A is after this F. It's a very simple thing. And at the end, for each sentence, what we have is we have this anim list of 1 to K, depends on how many phonemes we have for this sentence. And for each anim, we have a P, which is the phoneme label. and we C is we have this audio feature curve, E is emotion tag, and M is the motion capture, motion segment associated with this anim. Very simple. And so this database looks simple of the collection of the linked list, right? And we have so many thousands of sentences, so thousands of linked list. And of course, we have some kind of acceleration architecture, data structure to do the quick search. I just ignore that. So, for example, that's what we have. And then, given this database, let's take a look how we're going to do the search. Very simple. When we have input sentence, and we have the phoneme label of this input sentence also, right? We can so say this sentence, you say something, and we do phoneme segmentation of the sentence. So basically, we have this linked list of what the phoneme looks like for this. So the difference between this node and this node is this is anim node, which has motion segments inside, and this don't have motion segment inside because that's what we want to synthesize for the whole thing. And we want to match this input sentence which search this kind of database and find out what kind of motion we're going to use. For example, very basic matching searching criteria we're going to use is if you were saying the same phoneme label, the phoneme label is the same, the motion will be the candidate for this thing. For example, this P1, if there has another P1 into this motion capture database, we're going to put this out. That can be the potential candidate motion for this P1. Right? But moving on, so we can have, for this P3, we have two P3 in our database. So we have two different candidates for this P3, as same thing for this P2 and P4. So we had to find in this search space, solution space, basically, what if the P1 combination with this P3 combination with this P2 and with this P4, this is supposed to be one solution, and there's another solution. Basically, the combination of all this candidate. So the question is, what kind of motion is the best in this solution space? How can we find out? Okay, let's take a look what kind of potential sentence we have. So, for example, we can use this. So we say this P1 match, P3 match, P2 match, P4 match. So we have this output sentence. Basically, the motion from this P1 copy here, motion from P3 copy here, P2, P4. Then we do a little interpretation in between, and we have one sentence synthesized out because we have all the piece of motion in there. But take a look at this solution. What we have is, we have this thing called jump match. Basically, what does a jump match means? Basically, we're matching, then suddenly we have a jump from one linked list in the database into another linked list in the database. Basically, in this list, we lost call articulation. Basically, the context is not right. Basically, this P3 has to follow another. If there's another P2 in here, it's the best. So basically, and also the motion is not smooth anymore during this jump. And it's another jump over here. So we have basically two jumps in this database, in this solution. So the question is, we have to. It's not a question. The solution is how to minimize the number of jumps. So basically, what we have is this. So here we have two jumps. However, if we choose this P2 and this P4, suddenly we have only one jump, right? Which is a better solution for that. Have include more. Or call articulation information in there. However, if we choose this P3 instead of this, we have another solution with the same number of jumps. So how to solve this kind of problem, basically how to differentiate these two solutions. That's why actually think about this. We can choose this P3 or this P3. The very simplest way to do this is, okay, we say this P3 match this P3. And in here, we have the audio information, audio feature curves in here, and also for this anim too, because we recorded another sentence, this sentence. And simply we can say, is this audio feature matching this better, or this matching this better? For example, if in P3, in this sentence, we speak really loud and very slow, and in this sentence, we speak very fast, and it's not very loud, probably, in here is a loud one, we just probably matching this one because feature curves matches better. in there. And in that sense, the probability potential of the motion will be the best candidate for those. Another thing to find out is, of course, we have a jump match from this P3 to this P2. And we can say how bad this transition is. Maybe there's a big gap in between. And in terms here, this P1 to P3, the gap is not that big. So we're using these two criterions to find difference in between. So later on, we introduce a jump cost, basically, from anim to this anim. We find out what's the distance in between this frame, the first frame, the last frame of this phoneme I, and the first frame of phoneme G, and see how big the jump is, how big this gap is. And we can quantify how big this match. Or we're using matching cost, basically using the audio feature C here to say if this have a C in this and a C curve in here, and how badly this match is. And in terms of this, because we take a look at this feature curve inside I and anim I, the length of this segment might be different because in some input segment I speak slowly and there is a little bit faster, so it's hard to compare this different length of this motion. So we have using a dynamic time warping operator to move them together so we can compare frame by frame. Very simple solution. Then all together, so we're searching in this very complex database which this cost, so we minimize this cost, which is number of jumps. This is a very basic minimum. This is a major minimization we're going to do, and also together with jump cost and match cost to find the difference between if this two solutions have the same cost. But mostly this is a dominant factor. So that's a cost function we have. And basically, this is a very canonical problem of searching problem of how to search in a huge search graph, search tree question.
Why do you refer to that as a database instead of just a data structure?
We call it a database because some reasons we have a large number of animations initially, and we have all the audios and the pictures, audios and the tags and the motions all together. We put in a database, and later on, when we implement it in the computer memory, we have this data structure. So basically, we can call it a data structure in the computer and call it a database on the hard drive.
There's no metadata that you're collecting.
There is no other metadata we're collecting other than this 4 different features of phoneme label and the audio motion, and what's the next is an emotion tag.
How big are the elements in this thing?
One element, small element here.
Yeah, how big is each of those?
Each of those is, let's see, very tiny thing, probably about couple frame data. Each frame about how many? Each frame is a vector of about 400 long vector.
Is it literally a linked list, or is it a doubly linked list?
It's a single linked list, but
one direction.
Only one direction. Yes, we only have this one direction. We don't have other directions because in the search we'll find out. Because in the search we don't need this the backlink.
Okay, thank you.
So we have this data structure or database in here. Doesn't matter, but we have to search inside here and find a minimal solution. And there's a lot of algorithm already have depth first. Breadth search, A*, and here we just quickly use one solution called a priority queue, and this can be a little bit faster in here. But the problem is, even we do a lot of kind of things on top of this algorithm improvement, it is not a real-time solution. Why it's not real-time is take a look at this same matching, right? We have a solution database, we have potential links and a length of input. In our database, the actual database we have, or a data structure we have more than 10,000 of these nodes. And the input sentence length is about between 20 and 30. So you can imagine, these things will be exactly the one potential candidate is 100 for each node normally, and the length of these things will be like 20 to 30. So the solution space is huge. It's huge. Cannot so it's exponentially increased when this input sentence length is increased. So we cannot think about any good solution. Then we have implement our own real-time approach. Basically, it's a greedy algorithm. It's a greedy matching code. Let's see how it works. Okay, take a look at the cost function we have. So this is the dominant factor, we call the number of jump matches. So the first thing we do is we try to only use this cost function, ignore this because this is tiny. We have lots of experiments. This is a tiny factor. If we have two sentences equal number of jumps, we're starting using that. Other than that, normally the number of jump is the most dominant factor in here. So we want to minimize this. So our greedy approach is to find a solution without exploring the whole solution space. So it's not like we search all the branches in the search tree. We just quickly pick one branch and we know it is optimal if that is the case. How do we do this? So what is a greedy match? Okay, if we take a look of the input sentence, okay, so lots of phoneme altogether, right, one by one. And if there's a solution into this, basically it's a piece, it's a small section of subsequences, basically divided by the jump matches. It's all connected, suddenly there's a jump, and all connected, suddenly a jump. So for this solution, normally that is, if we have a t different subsections, so we have t minus 1 jump matches in here, right, if there's a solution. So normally what we do is a greedy match is such a solution that we want to choose the first one to be as long as possible. So basically we go into the data structure, say, let's go to match, find which match is the longest for the first one, so we go greedily for the first one. And we do that recursively so that the next one is also the next greedy one, so we always tend to find the longest piece. Give one example. The first match we find is like, if we match the first sentence with here, we have 3 matches. For this one, we have 2 matches. For this one, we have only 1 match that stop and stop and stop here, right? Basically, we get the longest matched subsequences when we put here, and that's our first part of the match we have. And we're starting doing the same thing for the rest of them, so we map P5, P5, and this P5 gets stopped here because it's not matched for P4, but this one has. So we get the longest again, so we get this. That's our final solution. Very simple, straightforward, but guarantee have the minimum number of jumps. And there is a proof which I'm not going to cover today. Basically, the idea is I construct optimal solution which is minimum number of jumps and give a greedy match solution, and I prove this solution and this solution is the same, basically S equals T. And if you're really interested, you can take a look at this into here and find out. Basically, using this thing, we can quickly go into that and pull up the most dominant factor and pull up the most dominant solution we have. And the extension of this work will be very easy to find all of the solutions with equally minimum number of jumps within linear time. Then we can compare them. And it's still not exponential, it's still linear.
I have a quick question.
Okay.
I'm wondering what the consequence of a jump is. Does that have a repercussion of the connections afterwards? So in other words, the best solution would be to minimize number of jumps in the very beginning, and then it would be okay in the end.
No, actually it's the same thing for that is you can start from end, right? You can do the longest backwards from end, then end, then end, then end. You can find not exactly the same solution, but as another solution guarantees also a minimal number of jumps too. But these two solutions, maybe one's good, one's bad. But we take a look at them, it's normally equal quality. But if somebody say, how can you find out which one is better, right? Of course, we can go back to compare these two things. So the good thing about this algorithm is another extension is we can go, when we have one solution like this, go greedy. Then from this one, within linear time, we can find out all the minimal number of jumps solutions out. So basically, it's because there's not only one solution with number of jumps is S, right? We have a couple of them. And with linear time, we can find all of them. And within linear time, we can compare between them and find out which one is actually the minimum cost if there is a big difference. But this is a good question. Let's take a look at some result I have. So in performance comparison, there's a priority queue is a traditional matching algorithm we have. So this interface, when I click on this button, motion synthesize button, starting synthesize a motion. But the same because it's very slow, I do 20 times fast forward here. Then I have the solution there, which 55 seconds takes.
That's all right. Tell me exactly what you think.
Using our greedy matching algorithm, there is a result very fast came out. Of course, I don't know if this number matters or not, but it's real time.
That's all right. Tell me exactly what you think. That's all right. Tell me exactly what you think. That's all right. Tell me exactly what you think.
They appear to be identical. Are they in fact identical?
They are not identical. So we ran a root mean square distance comparison between. So actually, the one test we used is we pull out one sentence from the database and use the sentence to test how good the thing is. And we compare these two results against original root ground root truth. Basically, the root mean square distance is very, very close. Okay, there's a couple of more of synthesized sentence using this algorithm.
I already regret riding buses. By working faithfully 8 hours a day, you may eventually get to be boss and work 12 hours a day.
Okay, so we just finished the first part of this algorithm. Basically, we know how to do a lip sync, and we synthesize animation, but the animation is a neutral phase animation. The second part is how to put expression on top of this neutral phase. Basically, answer this question. We have this neutral sentence like this, people talking, but we want to put actually the sad, if the sentence is sadness, in here and put on top to synthesize this one. And the solution is like this. If original motion is this M and neutral motion, and we want to map to another motion space in sad, like this, the first step we do is very important. If we can decompose this motion, original motion, into the motion of content, basically what you're speaking, and also into another component of style, basically what emotion it is. If we can do this decomposition, basically separate this into two segments, and what we do is we just copy with the content part into that, because the content part between these two things are the same. And basically we do a mapping. We produce a mapping function. This is the second step of these things, of only the style part into the sad part. Then we actually later on put them together. We have our original motion in sad space. Very simple idea. So in terms, first contribution we have is how to do the decomposition. And we're using independent component analysis and to separate this original motion into emotion and the speech components. And emotions components later on we used in emotion mapping and do the mapping, and we simply copy the speech component over, and we have our job done. first step, how to do motion decomposition. So first I should talk a little bit about what is independent component analysis. ICA actually is a linear transformation from two signals, and the result is they want to find out separate this original data into several components, and each component are statistically independent. Give one example. There's things you can find on this side. So, for example, if we have a room, have two microphones stay some places, and there's one audio signal is coming from a car, and this police car passing by, and another signal is from a television, a reporter reading some news. What we recorded here and here is mixed together, right? Those 6 signals are mixed together, and it looks like this.
The guardians of the electronic stock market NASDAQ have been burned by past ethics questions.
However, we don't want to do this. We want to separate them. Basically, apply ICA to this. We can separate them. It's purely the sound and
the
purely
guardians of the electronic stock market NASDAQ who have been burned by past ethics questions are moving.
The assumption behind this, because these two signals, when you collect them, are totally independent. There's something happened independently outside. There's a cars passing by. Inside this room is another thing. So these signals are totally independent. That's why we can use ICA to separate them. So in terms of how to understand ICA, we can give another two-dimensional example. ICA, to do ICA, basically compare with, we have to use a pre-processing step, basically using PCA to do this. So first step, for example, we have this data inside this two-dimensional space. The first step we do is PCA centering, right? Basically, move the coordinate system into the statics mean of this data. And then later on, we do widening. Basically, after widening, we actually rotate this axis. So the projection of this data into the new coordinate angles are uncorrelated. This is what PCA does. After doing this PCA step, normally after PCA step, we have to choose, we can do a dimension reduction, basically choose the first a couple of top component to have a most motion inside that. But actually ICA step does is, they do another transfer, basically apply a transformation matrix to convert this coordinate system into another coordinate system has more meaningful to cover the original space. So the difference between that is ICA doesn't require these two axes to be orthogonal to each other. So basically they have a better coverage to that. However, PCA normally makes sure that all the things are perpendicular to axes are perpendicular to each other. So we have this kind of more meaningful representation, and along each axis we probably have a more intuitive meaning for this data. And so between these two coordinate systems, we can use decomposition, basically transfer the original data X into our ICA space, in U space. And also reconstruction is, give us data inside our ICA space, we can reversely reconstruct this data. Applied to the facial animation, what we have is facial motion data looks like, this thing basically is chunk of motion. So each dimensional of vector will be the marker from 1 to n. Each marker has x, y, and z position, flowing time, trajectory, and we put them together as one frame, right? Then they have a lot of this data frames over there. When we get this data x, and then we apply this decomposition step, basically transfer this thing into our ICA space. So we have this component 1 to component m. If you notice that, and this dimension is reduced because for the ICA step, we do the dimensional space reduction, and reversely we can convert it back. But the idea is this. So remember, what we are trying to do is we're trying to separate the original motion into style and content. Basically, what is for your word speaking and what your motion is. Basically, we're trying to find the minimal information of this component. What does this component mean to us? That's a question we have to answer. Basically, we want to find out semantic of each component and classify each component into either style or content. If we can do that, we can separate them. Basically, manipulate U instead of original space X. So we have two ways to do this. Let's take a look at the visual way to do this. So first, we collect some data, basically some motion data, like
You
this.
can't hide anything from TV channels. You can't hide anything from TV channels.
Basically, this is two motions, right? The same speech, different emotion. We collect them, and we put them together and apply ICA. We get those components. And we want to know what's component associated with emotion, because there's emotion difference in there, and what component are related to the speech. So we apply ICA and we change one component. We have a 5 component here, and we literally change the value of each component, and we want to see what's happening. And by changing component 3, we say, this face is changing from happy to sad. So that component we classify into the style component, emotion component. And this one, component 1, when we're changing, is mostly like lower jaw motion. It's mostly related to the mouth motion, is speech motion. So that component is classified into speech motion. So after the thing, and also numerically, we can do the similar things, find out which component associated with speech and which component associated with style. And after the whole thing, we get a bigger picture of this. Well, what's going on in here? So we have the whole
Your
motion.
grandmother wants to talk to you. Toby threw the basketball to George.
For example, this is a constructed motion, and actually this motion is a collection of a whole different components. So for example, this component, those 3 components, lots of mouse motion happening, right? Compared with this one, so we associate with speech motion components. And this one is when we switch the emotion. That is the biggest difference. So this emotion components we can find out. And this other components we're not taking into account this time is eyebrow motions, and sometimes eyelid motions. When you blinking and you have eyelid motions, they can also detect it, separate them. So after this whole thing, we can separate the original motion into emotion and the speech. Then how to do the mapping? Basically, when we get original motion, for example in sad, we get one frame sad, F sad. We do the ICA, we separate them in the emotion components, of course, and speech. And what we want to do is, for the emotion component, we want to find a mapping function, map this thing into happy. Then we combine together with original speech motion. Then we put together as one frame in happy motion. Then we have a happy motion for the same content but different emotion. That's the goal. But the question is how to do this mapping. The mapping is done very simple. For example, take a very basic understanding how the mapping does is we have a original input space called X, and we have a space, out space, and Y. We want to know how this F is. What's the mapping between X to Y? That's our goal. So basically, we're using a data-driven approach. Basically, is instead of trying to understand that, we actually sample the space. Basically, we collect some data. We know X1 is mapped to Y1 for sure. X2 mapped to Y2, X3 mapped to Y3. And using all these mappings we collected before, we can do unsupervised learning to estimate how this F works. Basically, we construct a training set of X1, Y1 to X and Yn. Then we use this data to learn this function. Now our problem is also again divided into 2 steps. First, how to construct this training set, and how to do the mapping. To collect the training set is very easy actually, because remember we already have some motion like the 2 sentences with same content and different emotion.
You can't hide anything from TV
right, as usual.
You can't hide anything from TV channels.
When we have this 2 motion setup, right, like this, and we first apply IC on top, and we get emotion component, speech component for each set motions. And later on, we compute a time warping function. Why are we doing this? Because we want to get frame-to-frame mapping in our emotion. However, okay, I see you there. So what we want to do is we want to frame-to-frame mapping over here. Basically, we want to mapping from emotion component one frame to another. However, the motion we collect in the database doesn't have this constraint. Basically, we cannot tell, actor place 1.2 seconds, finish this sentence. We cannot do this. So the length of the motions of these 2 is not equal. So we had to learn a time wrapping function to wrap these things to actually to the same length. But how to do this warping? How to learn this warping map function? The good thing is the speech component. When we take a look at speech component, they should be exactly almost the same, because remember, these two sentences speak the same content. So I say I'm happy, and I'm happy, and I'm happy. The length is different, but the mouth shape, if you take a look, the mouth shape is very close. So we can use this component to compute a time warping function. When the timing function is computed, we can use the same time warping function to warp the emotional component, to align them together. Then when these things align together, and we can take this frame-to-frame mapping, this our xi, yi, and this our training set for our learning. And for the actual learning, we're using very basic radio basis functions to do the mapping. Basically, we have a kernel function. Phi is either exponential or Gaussian function, and we put them in and find out how to do interpolation. And we apply the original training set data into this function. Basically, we get a series of equations. And by putting these things, we can solve for our parameters. Ci is these parameters we're going to solve. Actually, this is a square matrix. It's a linear system. We can easily solve like this, and we can get a pretty good result. For example, take a look at one of them. There's all the emotions in here is mapped from original neutral motion.
Will you help me with my homework? I can't afford to try it again. She loved the pink skirt I bought her. When I got there, the store had already been closed.
Okay, so this is the final result I want to present. In this one, we have a long monologue. This monologue is several sentences, and they have emotion a transition in between. So we put them all together to demonstrate this system. Take about 1 minute.
No one ever liked me. When I was a child, we had a dance at my school on the first day of May. No one asked me to dance. No one. I went to the cloakroom and cried and cried. The teacher, Miss McFarland, I'll never forget her. She uncovered me and said, Otto, why are you crying? I said, no one will dance with me. And then she said, oh. I wasn't satisfied. That wasn't the comfort I needed. I asked her, why? She thought for a very long time, and then she answered me. No one likes you, Otto. No one likes you, and no one ever will.
Sad story, but I like this story, so we put them together. So in terms of summary, so we have this work include 2 pieces. So we have a real-time lip syncing algorithm and emotion mapping module. I just want to quickly go through some related project on the full body animation. This one paper we published also using ICA. So basically using independent component analysis, we can extract some style from these walking motions. Basically, this kind of style is a normal walking style. This style is kind of sneaky type of style. So what we can do is we apply ICA onto that, and we extract the style from that and do the transfer. Basically, this original motion, but I transfer this original motion style and put a sneaky type of style onto that normal walking kind of dynamic. And reversely, we can do the same thing. Basically, is a normal walking style put on a sneaky type of thing. And also, we can do this interpolation in between, changing from original sneaky to style motion. So it has a lot of power of this technique. It's also the running and running with sneaky type of style also can put on top. So we're doing lots of this thing, and the future research we do is we use this example is this video I got, this data I got from Electronic Arts. This is Tiger Woods' face and body. So this one, if we take a look, so it's not only the facial expression, all the gestures, the body movement, the eyeball links, and by looking this, so human behavior express a lot of emotion and style into that. And how to extract them, how to synthesize them is a very, very challenging task and very, very intriguing. So take a look at them, it's even a little bit dynamics different, but the eyeball is very sensitive. See how the board is like eyes a little bit close, and this guy, somebody asked me why they call it queen, and it's hard to answer, but it's like some stylish things we have over there.
So how do you define style?
Good question. So different people have different definition of this style, right? So even cultural make a big difference in there. Somebody you do happy, you say somebody from China say, oh, you're happy. Probably somebody in here you say, oh, you're not so happy. Those things. So this is based on our common sense of how to define styles. However, so in the machine learning or statistical model sense, there's just a motion in the style space. We don't know. We just call that one style. I mean, how?
But if you're collecting a database or collecting a number of
Yes.
motions, then you have.
Then we have to concern about this, because when we talk with this actor, say, could you please perform a sad or something, and he will use his own understanding of the style to perform that. So there will be an issue. So we can do lots of research on psychology to understand people. But in my research, I'm mostly focused on animation synthesis. So that's what I have. But I can learn lots from that too. Okay, so that's my talk. And if we have any questions, more, I'd like to answer.
Very interesting.
Thank you very much.
Yeah, really, really.
So this work, we're still working on that and trying to push into one of the game engine we're developing. Basically, have, one of the people, kind of social type of game, right? And you put into that, and people working depends on the current status of these things. They will be talking different ways, different emotions, and we apply this to that, and we can talk, different styles. In that will be very interesting to see. Okay, thank you very much.
Thank you very much.
Thank you.